Hey everyone, and welcome to Conf42 Golang 2025. I am Srinivas Vallabhaneni, and today I want to take you on a journey through one of the most promising areas in cloud security called confidential computing. We'll see how it's not just a buzzword, but a practical production ready approach to running secure workloads, and how Go happens to be an incredible tool for building in the space. Just to set the context, I'm currently a senior software engineer at Walmart Global Tech on scaling secure distributed platforms. Most of my work sits at the intersection of cloud native infrastructure, security, and performance. I work with tools like Go, Kubernetes, and various encryption frameworks on a daily basis. And that's why confidential computing caught my attention, because it allows us to design systems where trust is built in and not just assumed. And Go is a surprisingly good fit for that. So let's begin by talking about why this even matters. So over the past decade, our systems have exploded in complexity. Microservices, APIs, cloud, edge, etc. Right? They came into popularity, and there has been a wide usage of those in the enterprise industry. But with that growth, our attack surface has also grown massively. So today, the average enterprise sees a 2.5x annual increase in attack entry points. And here's the kicker. Nearly 80% of data breaches involve privileged access misuse. This means attackers aren't always breaking in from the outside, they're just misusing what's already trusted. So with that in mind, traditional perimeter security like firewalls, VPNs, IAM, which are widely used today in all the enterprise orgs, it's no longer enough. What we need is a way to protect data even when the infrastructure is compromised. That's exactly where confidential computing enters the picture. So, foundations of TEs. At the core of confidential computing are trusted execution environments, or simply TEs. Think of them as a lockbox inside your CPU, a place where sensitive code and data can execute, isolated from the rest of the system. Three things make TEs powerful. They are isolation, attestation, and encryption. Sorry about that. Let's talk about each of them. Isolation. Even if someone has root access, they can't peek into the enclave. And coming to the attestation, you can prove that only trusted, verified code is running inside the enclave. And lastly, encryption. Data remains protected at all stages, at rest, in memory, and during execution. So with all these, it's zero trust implemented at the hardware level. Now, here's the interesting twist. Why should we use Go in this space? There are many languages available, Java, Scala, or any other languages like Python, low-level languages like C, C++, Rust, etc. So TEEs are typically associated with C or Rust, that is low-level system languages. But Go is quietly carving a niche here. Why? First, Go has a tiny runtime footprint. This makes it ideal for running inside resource-constrained environments like enclaves. Second, Go's type safety and simple syntax reduce the chances of memory corruption or security bugs. These are huge wins when working in trusted environments. And Go's concurrency model with Go routines let us write parallel workloads that are still lightweight enough to run securely. So with all these, the balance Go strikes between developer simplicity and system level efficiency makes it a great fit for the domain. So now coming to the performance breakthroughs, right? One of the common criticisms of TEEs used to be performance. And rightly, early implementations were slow. Back in 2018, as you see in the graph, running code inside an enclave could add up to 35% performance overhead. That's a lot. But just 5 years later, we are down to around 4% overhead on modern hardware. That's a game changer, right? Combined with coarse efficient memory handling and low overhead, it finally makes sense to that the confidential computing is practical for production workloads, not just any prototypes. Coding inside enclaves. So let's talk implementation. How does this actually work in practice when you're writing Go code for TEs, right? The basic flow usually looks like this. You initialize the enclave, which sets up a isolated memory space and generates secure keys. And then comes attestation. You prove cryptographically that the code inside is what it's supposed to be. And once verified, you run your sensitive logic, maybe decrypting your data, processing it, or applying analytics. And finally, you seal the results, meaning they're encrypted before leaving the enclave. So Go's structure actually helps a lot here. It's easy to build clean state machines, modularize logic, and write secure tests around these stages. So enclaves and microservice architecture. Now, not everything needs to be run in an enclave, right? And that's the key. So let's take, for example, in a microservice architecture, there might be many services, and some might be very sensitive data, which needs to be part of the enclave, and some should be fine. Even if it is running outside and even if it is compromised, there is nothing much that we would lose, right? So keeping that in mind, in a microservice architecture, we take a targeted approach. For secure data ingestion, we encrypt data at entry. And for sensitive logic, like working with PII, personal information, we run it inside the enclave, and supporting services can handle blind processing on encrypted payloads. And finally, the authorized delivery phase decrypts results only for verified consumers. This modular security lets you protect only what's critical, minimizing the performance hit while maximizing data protection. Perfect. So one question I've heard a lot, I've seen a lot in different discussion channels around this topic is, can we actually integrate this into DevOps pipelines? And the answer is yes. And the tooling is maturing really fast. You can enforce attestation checks before workloads are deployed, and Kubernetes operators can now orchestrate enclave workloads using extended CRDs. And tools like HashiCorp support enclave-packed secret distribution. And with hardware support, secure boot, TPMs, and remote attestation, it's becoming feasible to run trusted workloads at scale. So with all these, it opens up confidential computing to cloud-native workflows, and that's a major win, and not just tightly controlled environments. So that gives us the advantage over the cloud-native workflows in setting up seamless integrations. And then let's look at a real-world scenario now, right? Like analytics on encrypted data. So the flow would look like we ingest encrypted data, say from users or edge devices. The data flows into a TEE-based analytics engine, and inside the enclave, data is decrypted, analyzed, and the results are sealed again. Only endpoints with proper identity and attestation can read the final output. What does this do? So with this proper flow that we discussed here, it creates a zero trust analytics pipeline, perfect for industries like healthcare, finance, or multi-tenant SaaS, where data separation and privacy are critical. All right, now engineering challenges. Of course, this isn't a silver bullet. There are challenges, and those would be side channel attacks. So these are still a risk. They require careful engineering and mitigation at both hardware and software layers. Then comes the remote attestation, where it becomes complex across large clusters or hybrid environments. And then key distribution is especially hard when dealing with isolated nodes, and secure channels must be established without exposing secrets. And designing minimal APIs between enclave and non-enclave code is critical to reduce data leakage risk. So all these aren't easy problems, but the open source community is making real progress. And projects like Enarx and Gramine and secure key orchestration layers are paving the way for all this. All right. So with all that, the next question comes, where are we headed? So the future is shaping up to be even more powerful. So we are seeing multi-party computation that will let us analyze joint data sets without ever exposing raw data. And then we have confidential containers, which will allow us to deploy secure workloads with minimal friction. And then specialized chips and TEE acceleration will bring near native performance. And all in all, zero knowledge proofs will let us verify correctness of computations without revealing any inputs. And with all these, Go as a language is evolving right along with it. It has the simplicity, speed, and structure to be at the heart of trusted systems in this new era. Great. And with that, thank you. I hope this session gave you a clear view into why confidential computing matters and how Go can be a key enabler of building secure systems that are cloud native and future ready. If you are curious, experimenting, or building something in the space, I would love to hear from you, and you can find me on LinkedIn at linkedin.com/in/Srinivas Vallabhaneni, or you can scan the QR code present here and you'll land directly into my LinkedIn profile. Thanks for listening and enjoy the rest of Conf42 Golang 2025.